All right, hey guys, welcome to lesson 1-2 in Algebra 2. All right, well, let's get started. We're talking about the properties of real numbers today. And so our objectives today will be, number one, to classify real numbers, learn the classifications. And the second thing is to use the properties to evaluate expressions. All right, so let's start out with a few definitions first of all. Real numbers. What is a real number? Basically, a real number is any number that we would normally use in real life, not imaginary. We will talk about imaginary numbers at a later date. Rational numbers will be able to be expressed as a ratio or a fraction. We'll go give some examples here in a second, but any number that you can write as a ratio or a fraction where the number on top and the number on bottom, you know, are integers. We'll talk about an integer in a second, but like 2 or 4, then that would be a rational number. If you turn a rational number into a decimal, it will either be a terminating decimal, which means it will stop, you know, like the Terminator. I don't know if you, the movie's kind of old now, but Arnold Schwarzenegger, you know, the Terminator. So terminating, what? Stops. The decimal stops at some point, like 0.25, it stops. That's a terminating decimal. And a repeating decimal will just go on and on and on. So 0.33333, that's a repeating decimal. Will just keep going. Integers, then, you could say would be whole numbers and their opposites. So that would basically be -3, -2, -1, 0, 1, 2, 3, and so forth, going both directions. Notice no decimals and no fractions on those. Whole numbers are just natural numbers and 0, so that would be 0, 1, 2, 3, 4, and continuing in the positive direction, but it does not go into the negatives. Natural numbers, people call those counting numbers. So when you count, you start with 1, right? 1, 2, 3. So it would start at 1 and go in the positive direction. All right, irrational numbers. Those were all rational numbers. Now, irrational numbers, they do not terminate. So you will not have a terminating decimal here. 0.25 is not irrational, it's rational. So if you have a number that's 0.216573329 and it just keeps going, that's irrational. Irrational numbers will not repeat. Okay, so you will not have a repeating pattern like 0.3 repeating, or, you know, 0.212121, nothing like that. Irrational numbers, an example of an irrational number would be a square root of an imperfect square. If you took the square root of 63, 63 is not a perfect square, it will give you a decimal that doesn't terminate and doesn't repeat. So anytime you see a square root of a number that's not a perfect square, it's irrational. And of course, the most famous of all, pi. Pi is irrational. All right, so let's kind of look at our chart here and kind of fill some of these things in. All right, so first of all, here in the natural numbers, I'm going to start there and kind of work my way out. I think I'm going to have to get something to write with here first of all. Natural numbers, remember, were the counting numbers. So that would be example like, ooh, I'm going to have to get a different color there. Let's go with, I think, what color do you think we want to choose here? I don't know. Now let's just try something kind of light. All right, natural numbers will be the counting numbers. So for example, like 1, 2, 3, those type of numbers will be natural numbers. Now, they're natural, but notice 1, 2, and 3 here are also in the circle of whole numbers. They're also included in the circle of whole numbers. So they're natural and they're whole, but they're also in the circle of integers. they're also on the side that's rational. So if you talk about the numbers 1, 2, and 3, they're natural, they're whole, they're integers, and they're also rational. Of course, and all these numbers here are real numbers. All right, so 1, 2, and 3 are natural numbers, whole, integer, rational, and real. All right, next. You know what? This is bothering me here, so I'm going to do one thing real quick. That was bothering me. Might have been bothering some of you too, so hopefully that'll help a little bit. All right, so let's get back to it here. Whole numbers then include 0. So for example, I'm going to put the number 0 in there. All right, so 0 is really the only number that's only in that section. So 0, 1, 2, 3, all of those are in the whole number circle. Then when we get out here to integers, that starts including the negative numbers. So out here we would have numbers like -1, -2, -3, -77, all those kind of numbers. But notice, all these negative numbers, 0, all the positive numbers, they're still all integers. Then when we get out here to the rational, these numbers here will be numbers like any fractions, like 1/2, 2/3. Notice, by the way, 1/2, what is that as a decimal? 0.5. Terminating decimal, it stops, 0.5 and then stops. 2/3 is what? As a decimal, 0.666. It just keeps repeating. So that's a repeating. So notice you can have a fraction, and if you turn it into a decimal, repeating or terminating is also rational numbers out there. And then also what could happen, I'm just going to take a step back here, is if you had the square root of a oh my goodness, if you had the square root of a perfect square, let's say you had the square root of 64, that would be in here in the natural numbers, because what would happen? What's the square root of 64? It's really 8. Okay, so whenever you have the square root of a perfect square, it ends up in that area. Let's jump over to irrational. Remember we talked about it's the square root of an imperfect square. So let's say we have the square root of 23. That's an imperfect square. It's not a perfect square, and so we're not going to get a natural number there, something nice and even. If you had like a decimal like 0.21379 ... and it keeps going, the ... means it's going to keep going, and you notice there's no repeating pattern there. That's irrational. And then also you have pi, of course, on this side. So those are the kind of numbers and where they all fit together there. All right, so let's just take a look at a few examples here. -1, where's that going to fit? What's -1? Think about that for a second. -1. Is it a counting number? 1, 2, 3, 4, 5? Nope. Is it 0? That would be where the whole numbers start. It's not a decimal or a fraction, so it would be considered an integer, and it's also rational, and it's also real. So it's real, it's rational, and it's an integer. It's all three of those. The number 6. Okay, where does that fall? Is that a counting number? 1, 2, 3, 4, 5, 6. Yes. So what that means is it's a natural number, whole number, integer, rational, and real. It's all of those. It's all of those things. It belongs in all those sections. Square root of 7? Ooh, we got a square root. Okay, is it a perfect square? Nope. So what does that mean? Irrational. It's a real number, but it's irrational. Here, next we've got 1/2. That's a fraction. All right, a fraction. Well, by definition, a rational number is written as a fraction, and so it's real, because all these numbers are real, and then it's rational, but it is a fraction. It's not a whole number, and it's not like -1 or 0 or 1. So it will just be real and rational. That's it. And then, of course, 0, we've talked about that before. 0 is the only number that goes just in the whole number area. So it's the whole number and kind of all the way back up, which means whole number, integer, rational, and real. It's not a counting number or natural number. And then last example here is negative 2.222. Is it a terminating or repeating decimal? Well, looks like it's a repeating. Well, I guess depending on how you look at that, that could be a terminating decimal. It could stop after 2, or it could be a repeating 2222. Either way, whether it's terminating or repeating, that's going to be a rational number, and so it's real and rational. I guess I wasn't as precise on that to tell if it was actually repeating or terminating. All right, properties of real numbers. Some properties. Okay, the fun properties. All right, here's what we got. Commutative property. First of all, this is an example of the commutative property of addition. Commutative property, if you, I don't know if you've ever paid attention to it, but on the radio sometimes you might hear them talk about, oh, the morning commute or the afternoon commute. That's when everybody's getting in their cars and going to work or leaving work and coming home. They're going someplace. They're changing places. So commutative property is when things change place. Notice in the first part here, let's see here, where am I? Oh, I'm writing in white. That's why I can't see it. Let me switch back to something I can see here. So over here, A plus B, A comes first, B comes second. But on the other side of the equal sign then, so what happened? A and B switched places. So that's the commutative properties when things change place. And this is considered the commutative property of addition because we've got adding going on there. The next example here, you notice 4 times 6 is the same thing as 6 times 4. The 4 and the 6 change places. And so it's the same thing, but this is really the commutative property of multiplication. So when you write those down, when you're asked for what property is, you can include the plus and the minus, or the plus and the multiplication signs there when you talk about those. Next is the associative property. Okay, when you hear the word associative, what comes to mind? Well, associate, maybe. What do you do when you associate with someone? You hang out with them, right? All right, so here's what associative property looks like. In this situation, the numbers or variables do not change places. It's in the same order. If you notice, let's look down here. No, here I am down here. A plus B plus C, A plus B plus C. They're in the same exact order. What changed? The parentheses changed. Over here, the parentheses were around A and B. Now the parentheses are around B and C. So what happened basically was B was hanging out with A, and then they must have had a fight or something, and then B said, you know what, I'm going to go hang out with C. So now B is hanging out with C. So that's the associative property. Basically, same order, but you group them differently. Okay, and again, that's an example of the associative property of addition. And our next one here is an example of the associative property of multiplication, because 3 times 5 is in parentheses, and then in the second part you have 5 times 2. In this case, 5 is the one that associated differently. Okay? A few more properties here. Additive identity. Here's an example of additive identity. 4 plus 0 equals 4. Here's how I like to think of it. You have something 4, you add something to it, and it keeps its same identity. It was 4, it's still 4. Okay, so that's the additive identity. You start with something, you add 0 to it, it keeps its same identity. Multiplicative identity. Kind of the same thing, where you start with something that has an identity. Here we have 8. 8 has the identity, but then we multiply it by 1. It still has the same identity. It's still 8. Okay, didn't change anything. So add 0 is additive identity. Multiply by 1 is multiplicative identity. Additive inverse, basically you're just seeing what two things add up together to equal 0. So in this case, I have 3 plus a negative 3 equals 0. You know, anything 5 plus a negative 5, 0. Anything that adds together to equal 0 will be additive inverses. And multiplicative inverses, one of my favorite. Here I've got 8 times 1/8 equals 1. When you multiply two things together to equal 1, and you might have heard me refer to this before as multiply by the reciprocal, if you remember that. So multiplicative inverse is the same thing as multiplying by the reciprocal. Okay, inverse and reciprocal really means the same thing there. Okay, couple more properties. Multiplicative property is 0. Just take something and multiply it by 0. It will always equal 0. Whatever it is, if it's 1,052 times 0, it's going to equal 0. That's the multiplicative property of 0. And then, of course, the distributive property, in this case, I have 9 times this parentheses of x plus y. And so then when I distribute, I mean, we've talked about this before. If I can find myself here. Oops. Let me go back there. When you distribute, you're going to go 9 times x. That gives you the 9x over here. Then you're going to go 9 times y, and that gives you the 9y. So you're just taking the 9 and multiplying it by each thing in the parentheses. That's the distributive property. All right, let's try to figure out some properties here. Let's look at some examples. First example we have is 5 equals 5 plus 0. What's going on in that equation there? I added 0 to 5, and it still equals 5, right? So that would be additive identity. If you notice here, I abbreviated this a little bit, and that would be totally fine. Additive identity. What happened in the second one? I have 5 times 2x plus 7. Well, if I look at that, I go, oh, well, what did I do? It looks like I took 5 times 2x to get 10x, and then I took 5 times 7 to get 35. That would be an example of the distributive property. That's, for some reason, a lot of times people miss that, so be careful on that one. Third example there, 8 times 7 equals 7 times 8. What changed? The order changed. Whenever the order changed, that's commutative property, and then notice I put multiplication in parentheses there. It's the commutative property of multiplication. Next example, I have a plus a negative a equals 0. Remember, whenever you take something and add it to something else to get 0, that is additive inverse. The additive inverse. Again, I've shortened that a little bit there. That's totally fine. Last example on this page, kind of tricky. This one's kind of tricky, okay? You look at this, you go, oh, there's parentheses. It's probably associative. Okay, be careful. Just because there's parentheses in there doesn't always mean it's associative. If you look closely down here, if we look closely down here, where am I? Here I have 7 plus 8 plus 2. Here it's 2 plus 7 plus 8. If it's going to be associative, the order won't change. But the order did change. In this case, what changed was the 7 plus 8. The 7 plus 8 and the 2 changed places. Those were the two that flipped places. So a little tricky here, but basically that's going to be the commutative property of addition. And why it's, in this case, it's all addition, but it's addition. The key thing there is because it's the addition part that they switched around. If it would have been 7 times 8 plus 2 in the first one, and then 2 plus 7 times 8 in the second one, this would still be the commutative property of addition. All right, couple more real quick. This is an example of the associative property. Notice 7, 8, 2, 7, 8, 2. Same order, but the parentheses moved. And so that's our example of associative of addition. 1 times v equals v. I've got this thing called v. It has an identity. I multiply it by 1, and it keeps the same identity. So that's the multiplicative identity. 2 over 3 times 3 over 2 equals 1. My favorite. Multiplicative inverse or the reciprocal, right? Multiply by the reciprocal. And then last one, 4 times 0 is 0. That's our multiplicative property of 0. All right, Last thing here, we're almost done. We want to simplify an expression. This is where we're using some of these properties to simplify an expression. You might not have realized that you use some of these properties when you simplify an expression, but you do. So let's take a look at this and say, what am I going to do here when I want to simplify this expression? Well, I see this 3 is outside the parentheses, so I said, well, you know what? I'm going to distribute that 3. We just did the distributive property. All right, so what does that give me down here? That gives me 12. 3 times 4x is 12x. Then I do 3 times 2y is minus 6y. I just did the distributive property. Now, I can do the distributive property again in the second part. Be really careful. There is a little tricky thing here on the second part. You have to think of that as being negative 2. So I'm going to distribute not the 2, but a negative 2. So I'm going to go negative 2 times 3 is negative 6x. Most people will get that, but they'll forget to do it on the second part. Negative 2 times y is negative 2y. Okay, that's the key part. That's where most people miss it. Now, technically what happens is this is where you might not realize you are using a property, but technically on the next step, what I can do is I can take this negative 6 right here, the negative 6x I should say, and move it so I have 12x minus 6x, and then I have my minus 6y minus 2y. So I got the x's and the y's together, and I did that by moving them. Now technically you say, oh, wait a minute, that's negative 6x. I thought it was the commutative property of addition, where you could only change the order if it was addition. And that's technically true, but what you can do here is whenever you have subtraction here, whenever you have subtraction, think of this as being plus a negative 6x. Plus a negative 6x, and I gotta go ahead. Sometimes these things run away on me here. Plus a negative 6x. And then again, you could think of this as plus a negative 2y. So as long as you keep that negative with the 6 and the negative with the 2, it really is addition. Okay, it's just kind of a sneaky way to do it. And then the last step here is, you can combine the like terms. Remember, like terms have to have the same variable with the same exponent. And so in this case, we have an x and an x. They're both raised to the first power. So I can combine them. Technically, I'm doing the distributive property here to combine these, but this is going to be 6x, and then when we combine the y's over here, a negative 6 and a negative 2 is minus 8y. And that's our answer. So you may not have realized that we used some of these properties in simplifying and solving equations later on, but we do. All right, well, that's it for this one. I'll see you next time.